sorry, speaking in Portuguese. A pointer and a slide, yes.
That doesn't work.
Yes, exactly like mine, so I know how to use. Okay. So it's up to you.
Okay, if we could move in for the last round before lunch. Okay, so we've now moved through the two presentations about what the perspectives are from the different countries, and now we've got 4 presentations on specific applications and digitalization technologies from us. And our first presentation is Professor Marable from Federal University of Rio Grande do Sul.
Yes. Very good. Hello, people. Nice to see you here. I am a professor in Federal University of Rio Grande do Sul in the Informatic Institute, but my background is in geology. I graduated in geology at URGS, and then has done the master and PhD in computer science, developing application, knowledge application for petroleum geologists. So that's my background. So our agenda is just try to motivate you about using ontology and semantic approach for interoperability in petroleum domain. It's became a buzzword, ontology, but we can discuss a little what I mean with ontology when I use that. How do you use this tool for interoperability as a conceptual tool, and some things that we have done and is being using for industry or is being developing in my lab, and some final remarks, and then I will introduce who we are, because if you are interested, you can know who we are. So I will let this to the end. So that's a common problem. That slide. That slides from the Energistic consortium that works trying to make the flow of information among many tasks and professional in reservoir evaluation. So come from well and seismic data and go into structural models and geological models and so on. I work more in this, doing facies modeling porosity and permeability, but I try to catch information from previous activities and feed the further activities and systems with this information. So what do we mean when you talk about Earth model, geological models? You know, it's a conceptual model, is an interpretation of the reality done by a geologist or a geophysicist when look at the domain. And we use these models to simplify the reality and to deal with this reality, also by hand, and also to be able to put the data inside of the systems. So the conceptual model is always like this. It's a person that looks through a kind of lens, and the lens is the cognitive, is the background in the mind of the person that helps them to understand the domain. And then he look at the domain and provide a representation of this domain. Of course, this representation is very influenced by this conceptual modeling inside of the mind of the guy. You need some previous modeling to understand the reality and to create your model. So the problem about the ontology is that we are modeling, this model in this is the representation of this conceptualization, not from this reality. When you try to integrate data and models, we pretend that what the models represent is the reality, but it's not. What the model represents is the understanding of someone regarding the reality. And then we have the problem about doing integration. What we do is trying to capture, to understand the main entities and entities connected to the reality through this cognitive filter, and identify this entity and map this entity through models. For example, I have a sedimentary unit here that will become a reservoir if we are looking enough. And then I try to identify this geological entity since the first models and data capture until the last model. To do that is that we use ontologies. What is ontology? I swear to you that this is a real picture that I took in Porto Alegre in a day of manifestation. I am not sure why the guys have written this in the wall, but it's true. I'm sure not. I'm sure not. That's very funny. I keep this picture forever. So what is ontology in the end? Sometimes we talk about ontology like an artifact, has a file, has a representation, but indeed, ontology is a logical theory to provide the connection between some vocabulary that we use for communication and the meaning of this vocabulary inside of a community. This is exactly what ontology is. It's a theory that helps you to express this map in a formal way. So when you use this theory and you create this representation, you have a domain ontology. So what the domain ontology is? When you have some strict rules to models the entities of the word or the entities of the conceptualization, you can create more precise models. And these models helps in provide the meaning of the entities in a legacy model or, I don't know, in the new acquired domain that we are studying. So ontology supports you in expressing in a formal way the meaning that is intended by a community when use some vocabulary. And we use to create standardization, like we are doing energistic and PPDM, to extend the usability because we have more precise models, and also to support interoperability. If you want to know better what is ontology, it's a nice paper. It's not written by myself. Unfortunately, I love this paper, which is called What is Ontology? And exactly this. An ontology provides a richer set of relationship, constraints, rules, blah, 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 that allows a more precise definition of some vocabulary, of terminology. So, what we use from this theory to improve interoperability? One of the things that we use is to use philosophical meta-properties to analyze legacy model or analyze the domain to do knowledge acquisition. One of the meta-properties is identity and another is unity. I choose these two. There are plenty of meta-properties that you use to analyze models, but these two are very important for geology. Why they are important? Because it helps us to understand the difference when I am talking about a geological object like a reservoir and a geological object like rock or some amount of matter. Why this is important? Because some properties that I have in a reservoir, it's not the properties of the unit that I am extracting oil, but the properties of the rock. And then I can extend these properties to other reservoir, other studies, or other studies, and other maybe sedimentary bases. When I am talking about the object itself, that has a geographical limit that has a size and has a shape, I have some properties that is only possible to apply for this object. Most of problems that I have seen in Earth models, in industry, is a problem that is a result of mixing these two objects. And then when algorithms try to extract automatically some further property, this mix results in wrong answers. Most of the problem is related to this. So we use this to identify what is a reservoir, when it stops being a reservoir, or before being a reservoir, and then we model only what we call rigid objects. It's objects that provide identity to the models and support the framework of the conceptual model. Other problems is when you deal with what we call amount of matters and holes. When I look like this, I am in an outcrop as a good geologist, I can see two things collapsing in the same place. One thing is the amount of matter that has some special properties, and the other thing is that like the container of the amount of matter that has geometrical properties. So I need to do this in a separate way to migrate this property to further models. Other problem is what we call relational dependence. Some objects in my models, to be there, they require to have other objects to be modeled. Then I can connect this model to other that's being created in other system. Like I cannot have a reservoir without a rock unit. When I define a contact between two units, the contact should be defined as an attribute of some entity, or is another entity by itself. What is this object, a quantity? What is porosity? I cannot have porosity without a rock, but we talk about porosity. Porosity is full of attributes and properties. Should I define porosity as a proper entity, or should I define as a property of the rock, or a property of the unity that I am modeling? This kind of discussion is supported by ontological analysis. And the result is that entities that are inseparable part of others should be modeled as an independent entity. What this means? When I model a hole, think about a hole in a cheese, okay? You can have a kind of cheese that's full of holes inside. You cannot have the hole without have the cheese. That's the case of porosity. But I can talk a lot about the holes. In ontology, I can assure you there is several books discussing what is a hole in ontological, in philosophical way. And the best decision for this kind of object that has existential dependence of others, but they are still full of personality, is to model this as independent entity, not properties in the models. Then I can migrate the properties of these objects that are of my interest to other models. So using this kind of tool, that is just a flavor, it's a short class of ontology, the shorter class of ontology of your lives, is just to explain why we understand when a model is worse than other or is better than other. So like this, I have rock, and then I have a subclass of rock that is a reservoir. What this is a bad model? Because a reservoir cannot be a subclass of rock, because a rock is amount of matter that has intrinsic properties that are different from the properties of a reservoir. So the best modeling of this is to have the geological unit, and then one of the geological unit has special properties that are reservoir, and then I model the properties of the rock, the amount of matter, and then I have the subclass of rocks. Just to make you get the general idea about using ontology as a conceptual tools. So good conceptual models are based on concepts that preserve identity, that can be countable, And then they provide the framework that we use to migrate properties between models and systems that are conceived for several different kinds of professionals with different knowledge background. We can count samples of rock and glasses of water, but we cannot count rocks and waters because they are not wholes. So we should make this apparent in models. So in ontology do that, improve model accuracy. So what I have done with this ontology-based applications, we use to produce persistence of data and ontology models in corporate database using relational database. And then we run application in other level in a separate way. And these applications are controlled by domain ontology. That's the general idea of the system that we have done. So we produce core description. This is a commercial product that started in my research group, and then we have a spin-off that is the Deeper company that finalize and commercialize the ideas of research that has some feature in terms of applications. So what we have done is to define a large, I can say large, ontology, domain ontology about rock properties in macro scale, in core scale, having an icon and the name of the property and the full hierarchy to describe this information. And then we produce a system to capture and to do machine learning over the information. Another, that's my PhD, a full ontology for petrographic analysis with the whole terms defined, and use this ontology to index people, to index pictures, to index, to describe rock, and use this for further processing by algorithms. So I can use the data modeling through StrataLedge to apply three different types of mathematics and machine learning application to do calibration of logs and automatic interpretation. So what I do is to training the machine learning algorithms to recognize the core description and the related pattern in the logs. And then I use to extract the analysis when I don't have the core description to have the exact interpretation of the geological facies. It's not only lithology, but it's facies with sedimentary structure, texture, fabric, porosity, oil presence, and so on. From the same basis. Then I can extrapolate exactly the properties of the rock to the rest of the well where I don't have the rocks, use machine learning. That's very fit to the basin that I am working with. This is the master dissertation of Vinicius Gracioli. Here I have the input of PetroLedge, controlled by ontology. I have automatic interpretation, use also machine learning of petrofaces. Petrofaces is a grouping of properties of the rock that are connected to quality of the reservoir, permeability and porosity. What I can show you is that this separation in colors were done by the geology, and this is the algorithmic detection. You can see some small mistakes here and here, but mostly the algorithm can understand, can separate without training the same petrofaces that Luis Fernando de Rose has done, which is our bigger expert in diagenesis. The same separation, there is a small difference. And the student is the Lucas Fernandes, is working with this in 5 months only. We have 1 year more to improve the algorithms to do that. That's the quality of the information. Okay, thank you. So we use for integrated visualization and analysis many mathematical methods and export automatic reports, including the model to HSQL using this information. So here we work with these people doing this kind of semantic migration of rock data. And that ontology development is a big effort. You need to do analysis, but it provides better models. And you can, when you have this done, you can have a very large options of application in that automatic interpretation of the properties of the reservoir. The advantage is that you increase the results that you can do using AI with this kind of information. So you can find the recent publication about this project on ResearchGate on our page of the group is database, intelligence database group. We are inside of the exploration production computer system group. And also we have a spin-off that is in deeper that finalize this kind of products that I showed to you. My profile in ResearchGate, you can find the papers. That's my partners on Energistic, Jean-François Renaud for IFP and Michel Perrin for I Call the Mean. And you can read more about this stuff in this nice book. Okay, open for questions.
We've got time for one question.
The field studies, where did the students make?
The field studies, because in my group, we have a cooperation with the Geoscience Institute. And then they have plenty of projects with Statoil, Petrobras, and Shell, and so on. What we do is just we take the information, take the ID of the information, took only the numbers and the description, and we use this for research. My students is computer guys. They don't, they don't understand. What we have is that we have some geologists that can have this information. We have now some complete set of data from Maersk that when they leave Brazil, they let to us to use a big report about Peregrino field that we are using. This data that I showed to you is all for Peregrino because it's an open report. Sometimes for do machine learning, we use not open reports, but we don't use the ID because we need only the numbers to see the results.
Okay, time for one quick question.
Yes, do you think that your ontology for your domain is unique, or you can have many different ontologies applicable, and how can you rank between all of them?
I will provide two answers. One has a research. The researcher used to say that the ontology of some domain is unique when you use philosophical and discuss the existence of the entities of the words. If you are looking in a glass of realism, you should have only one ontology. But what I showed to you is that you have a conceptualization and you model the conceptualization and you try to understand the meaning of the conceptualization of a group. Then if you change the group, you can change the ontology. In computer science view, we try to have a common view that can be supported by system. And a group of geology will have a different view from reality from a group of geophysicists. So I rounded around without an answer, but I answer your question.
Okay, great. And on that point, I think we'll have to move on. Thank you, Mara. And okay, and our next talk is from Jorge Luis Gonzalez. I hope I got the name vaguely right. And he's actually from this institution, so we're looking forward to that. over to you. You're okay.
Okay. Good morning to everybody. First, I would like to thank for the opportunity to be here. It's also my first time here in this Congress. My name is Jorge Luis Gonzalez. I am physics professor from the Federal University in Espírito Santo. Also, I am participating in a project coordinated by Professor Marcio Albuquerque here from CBPF. The staff of professors, including also students, are also from CBPF. And I would like to show some work we have done in the last 2-3 years working on image processing, classification, and also simulation of rock properties in multi-scale. Okay, well, first I would like to show you some main research areas we have worked in the last years. These include some domains as scientific instrumentation, X-rays, imaging techniques, also processing, imaging and signal processing, high-performance parallel computing, artificial intelligence, and finally we have statistical characterization of heterogeneous media. It's a rock in a sense, and some kind of petrophysical simulation in this media. We have some recent publications, like for example, representative elementary volume for nuclear magnetic resonance simulations. It was, this manuscript was submitted to be considered for publication in Journal of Petroleum and Science. Master in physics and artificial rock by using a random cross-packing model. Also segmentation of microtomography images of rock using texture filtering and so on. The principal domains of our work can be classified or include some works like, for example, discrimination between pore space, grains, or different phase in the study media, the estimate of petrophysical property directly on the image, the register and correlate imaging obtained through different techniques, like, for example, X-ray microtomography, scanning electron microscopy, and the characterization of Borehole profile, and also statistical characterization of pore extrusion and petrophysical simulation process in the three-dimensional images. In a sense, the project is separated in 3 great areas. The first one is the signal and image processing, include machine learning, for example, extraction of characteristics of grains and pore geometry. The second area is the characterization of borehole profile using advanced techniques to detect fractures and clustering and facies classifications. And finally, we have the complexity and statistical physics applied of this media, like, for example, the use of the statistical descriptor to characterize the media, the porous media, and the simulation of petrophysical properties. Now, before to continue, so I would like to show you some examples of work done in the different areas. For example, regarding the first area, we have developed a software with name Attritex. How this software works? The user enters with the micro CT cylindrical plug image, also medical tomography image, in even optical microscope optical image, and the software provides some property of the image, like, for example, enhanced image. You can select a region of interest. The pore or grain segmentation means to separate different phases in the image, porosity values, and texture classifications. This software was developed in our group. In our group, and for example, here is another example of the work developed in through this software. For example, you have here can put this. It's not working. I need to point laser. Oh, okay. Here, for example, you have an image. This image can be separated into phases, the pore space and the solid phase. And what is interesting is you can introduce a sub-resolution image into the original image in order to capture the absence of the fact that you have limited due to the resolution of the image. And then, for example, this porosity is 4.2 around percent is the porosity of the original image after segmentation. Here, if you introduce the resolution porosity, you can obtain 8.5% of porosity in the total, in the complete images. And this porosity in the image introduced in the subporosity resolution is of the same order of the porosity determined by experiments using porosimeter. Also, you can introduce a region of interest in the image. In this region of interest, you can determine, for example, pore size distributions, the system of different phases, and so on. Regarding the second area of interest of our project, we have, for example, the Borehole image enhancement and processing of image of Borehole. For example, you have here 4 different images, this one, the other, the third, and the fourth image, original image of Borehole's experiments of acoustic measurements in our system. These vertical lines are noise due to the experiments. If you want to reduce this noise, it will this reduction of the noise, it is important thing in order to analyze the real data from the acoustic measurements. And for example, this algorithm was developed in our group in which you can remove this vertical line of the noise of the acoustic measurement also. Here we have also acoustic measurement in an algorithm. An algorithm was developed in our group where you can detect the existence of fractures and breakouts in our acoustic measurements. Also, in the second area, you have this kind of measurements, of acoustic measurements. The blue lines represents here is the permeability as a function of the depth of the borehole. And here, the blue line also in the lower part represents the effectivity porosity as a function of the depth along the borehole. You can select some small set of points, experimental points, to train a deep learning machine, or neural network. After that, you can predict using this neural network different predicted points along the borehole depth. And these points, the predicted points, are the solid circle here shown in the upper part and also in the lower part. As you can see, there is a good correlation between the experimental points and the predicted points. Here in the left, in the right side, we have the predicted values as a function of the original values. As expected, the points can be described by a linear fit with linear coefficient around 0 and angular coefficient around 1, which means that exists a good correlation between the predicted value and the original value. This is true also for the porosity, for the effective porosity, and for the permeability petrophysical property. Finally, we have the third area. Here we have the porous system as a complex system, which means that porous rock, for example, are heterogeneous media where the physical property and microscopic scale are completely determined by a microscopic process inside the system. As microtomography provides a pore representation of the rock by using the segmentation described in the last slides, we have a pore representation and, in particular, its morphology, which can be characterized by using statistical descriptors. Once you have the pore representation, you can use simulation on this, or basic on this pore representation of physical or petrophysics phenomena, like, for example, permeability and many other petrophysical properties. The objective of this point is to establish correlation between macroscopic physical property and the morphology of the rocks. Then I will try to show you some examples of what it means for us a simulation of these petrophysical properties and the statistical characterization of these media. This is a natural rock from Lagoa Salgada. Using different statistical descriptors, you can establish, for example, the area to volume ratio of cluster of pores inside the natural rock is shown here. Also, it's possible to compute the autocorrelation function of the pore space, as this function shown here. What is interesting here is, for example, there is some theoretical model in which you can that try to put a correlation between important petrophysical property, like, for example, permeability, as a function of this kind of autocorrelation function. Usually, this function is identified in the literature as two-point function. For example, another example of how to describe the statistical property of an image. We have, regarding the last image, we have, for example, the fractal structure and the multifractal structure. Here again, we have to point it to the fact that, for example, the image porosity seems to be better correlated with the multifractal structure as compared to the fractal structure. This is also important because it means that in some sense, the multifractal structure can be more correlated with the pore structure of the analysis system. Here we have another descriptor, another statistical descriptor. In a sense, it's the pore size distribution inside the last sample. And this is some kind of gamma behavior from a mathematical point of view. But in any case, we have the possibility to use the image to describe, to characterize from a statistical point of view different descriptors, using these different descriptors. Here we have another example of simulation and also statistical description. The same rock here from Lagoa Salgada. This is experimental nuclear magnetic resonance measurements. From this experiment, we have to found a distribution of relaxation times in this through this decay of the magnetization. And here we have a simulation using the pore structure found in the last using the last statistical descriptor. Here we have, for example, the simulation, and if you put attention, there is two contributions to this decay. The first, both contributions are exponential and also including relaxation time, which are included here in the experimental results. This simulation was performed by using a discrete random walk algorithm, which is very common in the literature to describe a nuclear magnetic relaxation phenomenon. Another example, for example, you have here the same relaxation, but now looking at the point that how the data population can modify our results. This is different simulations here for different volumes of data analyzed. Here, for example, this is a small volume. You are increasing the volume going in this direction. And what is interesting is the system of representative elementary volume above which the simulated data can represent the whole system. This is interesting because, for example, from nuclear magnetic resonance experiments, you can detect or you can found an important petrophysical parameter. In a sense, the area to volume ratio of the pore structures. And here, for example, if you analyze our simulated data, you will see that this parameter start to decrease and going to the base value here, which for me represents that above this volume, you can be sure that, for example, the found experimental value from the analyzed system is representative of the whole system. Here, the same effect, but now observed through porosities. If you try to determine the porosity in the image, you will see, for example, that the different porosity for different volume of the analyzed system image, and then these porosities try to converge to one defined value here around 0.2%. Also, we have tried to simulate an artificial rock, but using different statistical models. For example, here we have a random closed packing of spheres. In this case, the spheres, each one is penetrate into the other one. The point is, we have this artificial rock in principle. We have the natural rock here. Both systems have the same porosity, but the fact is, in spite of that, the morphology of the pore structure in both systems are totally different. You have here, for example, this red line represents the autocorrelation function of our simulated system, the random closed packing, and this black square represents the autocorrelation function of our natural system. Okay, I will finish. As can be observed, there is two differences in spite of the fact that both systems have the same porosity. The question is possible to get an artificial system with the same porosity and also with the same morphology of the pore structure? The answer is yes. Using a metropolis algorithms, it's possible to get the box system, the natural and the simulated system with the same porosity, also with the same autocorrelation function. And as I said at the beginning, the autocorrelation function is very important from a statistical point of view, because there are many petrophysical properties which are well correlated with the function. And here we have, for example, the blue line represents the natural system, the autocorrelation function of the natural system, Lagoa Salgada, and the red point represent the autocorrelation function of the packing of the random closed packing after the application of these algorithms. Finally, I would like to show you, to point out to the fact that in spite there is many work being doing at the moment regarding the digitalization of image digitalization, we have some interesting open questions, like for example, how high performance computing, in order to include a big data in the analysis, statistical physics is possible for statistical physics to get some kind of correlation between the property of low scale system and the property of a higher scale system. This is a question open at the moment for us. I would like to thank to everybody for the attention. This is.
Thank you. We've got time for a question.
Thanks for the presentation. Vinicius from Technip FMC. Regarding your work with data classification and pattern identification, well, I saw just what type of algorithm you are using. I saw k-means. It's a type of data mining algorithm.
Yes,
it's an old one.
Regarding the face classification in the image, we are using our group. Really, guys, our group is using
The next slide, yeah.
yes, different classification algorithms. For example, this one is with using k-means algorithm and three-phase. But also the others, the group is using another algorithms to classify the image.
Do you just to point out that Google guys and Facebook guys, just a professor like Ian LeCun, they developed convolutional neural networks that they are the cutting edge for image pattern identification using inception models and so on, pooling layers and so on. Maybe it can you can test that into your research and can extract more features and then improve your accuracy of your model. But very nice work with that. Just a simple algorithm that could give you some responses.
The group is using this software. You have the opportunity to select different classification algorithms. Depends on the algorithms you will find different results. This is the idea.
Okay, great. Thank you very much. And I think we'll have to move on to the next paper, but round of applause for you. Okay, I'll try to double multitask on this. Next paper is about something that was identified very much in Ismail's paper as being something that will be of relevance to the industry, which is called cognitive computing. And we've got Emilio Vital Brazil from IBM who will be telling us about that.
Hello. Can you hear me well? Yes. No? Maybe. Hello? Better? Okay. I'm Emilio. I work at IBM Research, Brazil. I'm very glad to be here because my history with oil and gas industry starts with Norway. When I finished my PhD thesis in math, I'm a mathematician, did here at IMPA. I was invited to go to Norway to work with CMR Foundations. I think it's a foundation. They have a project, and they want to use my PG code in this project. Then I start to work with these guys for the oil and gas industry. It was very interesting start, and now I'm here again with the Norwegians, and it's very good. I will talk very little about the IBM research, because normally when you talk about the IBM, you think the big tech a company that has now 107 years, but not everyone knows that we have a research division. In fact, one of the most old research divisions, industrial research divisions in the world. We have many awards in our staff, like 6 Nobels, 10 national medals, 5 national medals of science, and 6 Turing awards. And we have many discoveries and inventions in different areas. We don't only work for applied science. Sometimes we are have some, or not sometimes. In fact, we are incentivized to work in our fields and bring the base science into the industry as well. One of my favorite IBM research was Madebro with the fractals, because he was a mathematician like me and worked in this very beautiful result of fractals. It's fantastic, this one here. Nowadays, we have 12 labs around the world. It's one division with 12 sites, or not 12 sites, 12 labs. Here in Brazil, we started at 2010. Now we have about 70 researchers, and we have 2 sites, São Paulo and Rio. And I'm here in Rio. We have these 4 main groups. That's the first one is natural research solution, social data analysis, visual analytics and comprehension, industrial technology and science. Okay, but all are aligned with this cognitive and cloud strategy of IBM, and that's the main areas of research now. I am in this group here with computer vision visualization, but I work a lot with natural research. I come from IBM to work doing the bridge between these 2 guys here. That's my main focus now. Our 3 main industry here in Brazil: oil and gas, healthcare, and finance. Okay, I will talk a little about this, our cognitive platform. And that's our research agenda for oil and gas. And that is not only a product or specific research. We think that's as a platform. We try to involve different areas, different subjects, and different knowledge inside that to create a whole platform that allows us to plug things that we believe that are important for the industry. Okay. Today I will talk about some use case to illustrate the concept of digitalization that we are talking here. And normally we have these 6 basic use cases that we use to illustrate our ideas. As I have the luck to speak after Professor Marabel, I will be able to skip the first one because we have short time. In fact, I have to thank Professor Marabel because one of her former students is working with us now, Joel, and he was working exactly in this part of Bayesian reservoir knowledge builder. Then, thanks, Professor. It's really great to work with Joel. He's an amazing guy. Okay, then I will be focused on these 2 here. That's the seismic interpretation and Bayesian reservoir similarity analysis. Okay. But again, just instance that what we have working. The idea is have the platform for the subsurface characterization. Okay, let's start with the use case 2. That's one use case that we have been working for a while. We start with the question of how to help the interpreter with the task of understand the subsurface when you have some images or some information about that. I believe for the audience here, seismic image is not something new, but we know that they have a lot of uncertainty, and it's an interactive process. We start with some model in your head. You start to do some hypotheses. You test your hypothesis. You discuss your hypothesis. And the question is how you can help this interpreter in this process, and how we can capture and give back the interpreter test knowledge in this process, how you capture that, and how our tools could help in this process. That's it's not something that someone should be sure about the information, something that you need to create hypotheses, go for your colleagues, try to validate, and you probably never will be sure about that, because if your hypothesis is a dry reservoir, you don't drill that, then okay, maybe it's not. But that's the main question for us here, is how you could help for that. The example that I will try to explain today, it's the integration with the image algorithms, how we could bring computer vision for this process, helping the interpreter. And I say helping the interpreter, because I could be here saying, okay, we're trying to interpret the image, we try to give the answer, but for us, it's very important to have the human factor in the loop, and that's bring many interesting research and how we could work with that. Okay, we have some cases of applying that for medical image, but it's not the same. Despite of the nature of the image could be very similar in the sense they are based on a sound, and it's not a direct measure, but when you are in a medical image, for 99%, you know what you're expecting, okay? It's only 1% that you, okay, something unexpected I will see. And this side's opposite of that. When you have the image, you don't know what you are expecting. Then, for me, that's not a geologist, always that I look this kind of image, I think that's something that's impossible to extract information. Then, when geologists start to explain me, oh, here you can say that you have this different color here, that means probably an anomaly of amplitude. And I can suppose that, then it's much more suitable and much more, the model that you haven't had should fit what you are seeing, and you need to change your model again. That's something that's, for me, it's very exciting. Okay, then, but it's not only bring visual comprehension or computer vision or imaging processing. What you call vision comprehension is the union of these three things here. You have the practice, okay, how the guy works. You have the technology, machine learning, deep learning, feature characterization, and you have the knowledge. As Professor Maribel said, you need to a vocabulary to work with that. You need to try to narrow your possibilities and communicate that well. And more than just bring a feature of one image, you want to feed your knowledge, okay? And for sure, inside of the parts of the expert. Then, this project here that we have been working for 2 years now is creating this cognitive visual computing for getting image structuring for seismic image. Why I'm saying image structuring, not geological structuring? It's geological structuring something, okay, a salt dome or a fault set, something like that. Here, I'm trying to understand the whole picture and try to classify each part and build some structures for the user, for the experts, okay? And when you talk about that, you need to knowledge engineering, image structuring, and cognitive interface together. That's what we call cognitive visual computing or image comprehension. How we see that should work? We have the image here, the seismic data here, the amplitude, for example. We run our algorithms with the feedback of the expert. The expert will be in all parts of this process. We get information, feed one knowledge base. This knowledge base, again, should bring information for the expert, and you close the loop. For the other side, you can use mathematical properties characterization, create new data, or a different kind of data, like inversion or this kind new information, and then feed again and use it all together. And with that, we can, for example, start with very simple tasks like recognize one part of your seismic and say what is that, and bring more like that. Or if you have different information, for example, if I have an inversion for this part, I can bring together and say, okay, that's for sure a salt dome because in my inversion, I can see a different patterns. I can combine that beyond the interpreted eyes, because normally you won't see one image. We can see 4, 5, 10 images in the same time and bring the more relevant information for you. Here, just to represent the information flow, here we can imagine that we start with Professor Marabel's work, that we have ontology, you have some paper information, some knowledge start from the literature. Like, for example, I want to understand better a basin. That's my first case. Then I have ontology that describe my base. Then I go to literature to capture this information and organize that. That's one way that my expert can consume. Then he's had some hypotheses about the basin. Then he can start to think about the model in the seismic image. We can bring more information for the scenario. Okay, now I have a more complete model for my scenario. That's the case that I'm working here. Okay, then I go for the next step. Okay, ooh, 2 minutes. I need to go quickly. Sorry. The next use case is I have some structural data. I have some information. I want to extrapolate that using my knowledge base, my information for former projects, or compounding with my basin model, with my seismic interpretation. But I have this data and I want to complete that. This work is about how you can bring analogs to the expert using statistical analysis inside the structured data. But to compound your structured data, you need, again, one ontology. You need your data well curated. But normally you don't need only that. You want to bring more information for outside of your company. That's where, again, you can go to the files or the articles and bring inside your database. Okay? Then you can have these 2 lines of data that you can observe. First one, the internal data that's already integrated, it's clean, but probably you want to do the second one. You have report, articles, you want to have the same thing. But the question is, not only how to integrate that, but how you create that, how you maintain that, how you keep the history of that to be, when you take a decision in the end, you can say, okay, I'm taking this decision because I have this information here, and I can trust this information because it comes from this search. I need to skip the video, sorry. But the video just illustrates the system working. And the final part is, okay, now I have my reservoir characterization. And in each step here, I can come back and say, okay, I'm taking this decision here. And why I'm taking this decision? Why that's a wise decision? Because someone get this information from a good paper on my database, and that's come from a good interpretation, and this interpretation have a good machine learning analysis, and that's what's based in a good ontology. That's kind of trace back that's important for your decision. You don't need more take decision only the numerical part, but in the whole history of your data. That's one thing that we believe that's very important. Just to sum up, cognitive computing, it's a very powerful tool. It's not totally solved. That's why research is involved. We have many pieces that works very well alone, but put everything together is not so easy like looks like in the first moment. It can solve big problems, but we need some effort, of research effort, to solve that. And this integration and this possible follow your trace of information inside your process, it's very important. I think it's that.
Hello? Yeah, good. Thank you, Emilio, for a presentation. We've got time for one question before we go on.
Hello, thanks for the presentation. I have heard that IBM was working with Woodside Energy in Norway regarding...
Australia.
Australia, oh, okay. So can you say a little bit about it? Because it's a different application about
yes.
products.
Yeah, it's in fact, in this application, it's different. It's not research. It's what we call GBS. It's a Watson group. Because, come a little about the history of Watson. Watson, it's a brand, IBM brand. That means it's something outside research that started in research when the first time that Watson appears in the media was in the Jeopardy. In that time, that was research. Then they start a new brand for apply the research technology for industry. The first industry was the medical one for help experts to understand the diagnosis of cancer, suggest treatment, this kind of thing. Okay, this is a different brand. It's not research. As it's not research, normally what you do, you get what we have developed and apply for the industry. You don't develop something really new. You just get from the shelf and apply. This project of Woodside, yeah, in Australia is about that. And it's a very successful one. It's a very, very interesting one. They create this dialogue mode to ask. I will show, my video show a little bit about that. You have the free dialogue mode that you can ask for the Watson, some information about fields, I believe. I'm not really inside this project. I just saw some videos, and they answer the papers that you have. They answer the question and show you the paper that could have the answer.
Okay, great. And at that point, we'll move on to the next presentation. Thank you, Emilio. Okay, and it's now my pleasure to hand over to my co-chairman for the session for the last presentation between this and lunch. And that is Professor Duarte from Federal University of Rio de Janeiro. That thing goes.
Hello. Now we are changed because my field is not computer science, nor geology, nor petroleum engineer. My field is ergonomics. And my presentation is about a specific field of ergonomics, known as activity-centered ergonomics, or constructive ergonomics, and its recent development. I work with petroleum gas. I have worked with petroleum gas industry since the 90 years, and first with refineries, and nowadays with digitalization in oil platform. We have used this approach, constructive ergonomics, in recent projects of integrated operations with the Brazilian oil and gas industry, mainly with Petrobras. My presentation is divided in two main parts. The first part is more conceptual. I will present the central ideas of what we call constructive ergonomics. In the second part, I will present a case of a project of a collaborative work center. Since the beginnings, ergonomics has set its goal as fitting jobs, environments, and machines to the humans. The symposium that led to the creation of the International Ergonomics Association, which took place in 1967 in Netherlands, was called Fitting the Job to the Work. Today, this goal certainly remains commendable, but it's no more enough. Nowadays, face of the new technologies, digitalization, for example, and the frequent organizational changes, the objective of ergonomics is development. Develop what? The development of individuals, construction of know-how, knowledge, and skills, and development of organizations based on integrating within these organizations reflective processes that are open to the workers' own capacity for innovation. Activity-centered ergonomics was built on a model that distinguished a task or prescribed work from an activity, the real work, the work practice. This model views an activity as the product of a continuous process that takes place within the subject. In this model, the operator is viewed not just the person who carries out a task, but as the creator of his or her own mobilization. This mobilization relates and articulates, in a given context, the requirement of the task and the will to preserve himself, to succeed, and to learn. The operator regulates his or her activity depending on the results it produces, in terms of both achieving task goals and the effect this activity has on the operator and on collectives of operators. the design process is seen as an opportunity of dynamic of development and requires a mutual learning involving designers on the one hand and future users or operators on the other hand. A methodological consequence, the activity participation of individuals in the design process is not additional or optional feature of the methodology. It is necessary to ensure the consistency of a constructive approach. The artifact and concept, a central concept for this approach is the concept of instrument. Instrument is an object plus a use schema. The artifact is a manufactured object in its material and symbolic aspects. The instrument is a composite entity that comprises both an artifact and a component related to action. It is the association of these two organized in a system that forms the instrument. For example, a pen is an artifact that does not in itself form an instrument. In order to be an instrument, it must be associated with organized forms of action that are indeed the object for a long learning process in children. In this association of the two that allows writing. Therefore, during design process, such as integrated operation center, it is a coupling the systematic organization of two entities that constitute the object that is being designed. In the practical sense, designer and workers contribute to design based on their diversity and all competence. From the point of view of methods, the focus must be on the dynamics of the exchange between workers and designers in order to facilitate and provide to support them. It is in this view what we speak of a dialogical approach of mutual learning. This dialogical model provides a very different vision from the classical approach of engineering, where design is viewed as a change of state during which problems must find a solution. In dialogical view, design appears not to have a true starting or finish point. It is instead a cyclical process where the results of the work of the one person, designer or worker, fertilize the work of another, and where there is probably no such thing as a last word. Activity-centered ergonomics approach has developed over the past 30 years an approach to supporting design projects that combines ergonomics work analysis, a participatory approach, and the simulation of work. It can be reported that this approach, when specific conditions are present, contributes to the development of activities and not just to design the solution that they are expect in the project. This constructive dimension is not just a positive effect induced by this approach. It should be considered a driving force of the ability of men and women to cope with changes in their work situation when they can actively contribute to design this situation. The simulation of work plays a key part in this process. In activity-centered design, design projects are concerned less with defining the characteristics of artifacts, products, tools, space, workstation, and more with defining the feature of the work situation in which these artifacts will be present. Indeed, in a work situation, activity is deployed within space that is framed by a set of prescriptions, tasks to be carried out, workspace, hardware and software, and organizational structure, formal allocation of tasks, schedules, rules, trainings. The design of the work situation then focuses on defining these various components and the relation between them in order to allow the deployment of an activity that is effective and protective of the health of workers. Ergonomists should not focus just on provide input in form of recommendation to process for design artifacts that are mastered by the designers alone. They should instead contribute to implementation of a global structure approach, a real approach to innovation within the company in order to move from a project that is managed based on technical criteria to one that is managed based on future work. Now, our example. This project is a part of a PhD research developed by Nora Maia from SEMPS at Petrobras. This intervention was carried out by our research group formed by me and other two architects and ergonomists. We carried out an ergonomic intervention during the process design of the Integrated Operations Center. Our study was developed for the subsea department of the oil and gas industry. In fact, the new production fields like pre-salt in new other production areas request efforts to improve vessel services. So an ergonomic study was developed for a workspace, including layout, lighting, software, and the collaboration with informatics engineers. The aim was the integrate of different sectors or department. Why? To share the available resources that are different kinds of vessel that you can see, to reduce costs and mainly increase the utilization rate of vessels. In this collaborative work center, we work nowadays 4 teams of operators from 6 different departments of subsea service. How was the methodology? The first step was the agronomic work analysis and pilot projects. The objective was understanding workers or users' activity in real situation. Activity work analysis are made for the different teams: monitoring, control, and technical support, planning and programming, logistics, supervision, and operational performance control. The simulation scenarios were constructed from the technical action situations, monitoring of real-time operations, material and human research. So the real situations, typical action situations, are the scenarios for our work simulation. And the simulation for us is a kind of meeting. You know, two kinds of meetings. Meetings by sector and meetings with the committee representative and project leaders. During the meetings, we use PowerPoint presentations. Initially, the ergonomists showed the criteria used for the layout studies, blueprints with the location of each workstation, and scenarios that characterized the activities of each sector. From the initial presentation, the layout was modified by the participants, and new slides were created to changing the workstations. All meetings were audio recorded and analyzed after. So this is the beginning of the project, and after 10 meetings, they changed completely. For the conclusion, or for some points for discussion, the collaborative work in this case is characterized by actions to face many unforeseen events, unforeseen of various and different natures, sea and weather conditions, tasks not planned, conflicts among procedures, and others. And the articulation between individual and collective dimensions of work. To design collaborative work center is to redefine work organization, mainly manpower, and redefine ways to work collectively. Project manager may support or not the development of the work activity. Saying the other way, participatory project management and the workers' engagement through the simulation process made possible, in this case, the development of the new ways of working and change in proposed layout and the software that support this activity. Thank you.
Thank you, Francisco. We've got time for one or two questions before we go to lunch. Okay, I've got a question about, you've got a specific research area in ergonomics. We've got lots and lots of technical projects. How do you see that we can get those projects to work together? Can you use us as experimental rabbits, for example?
It's very different fields, but I think we try to do, we need for work the real situation. Without this real possibility to improve activities, we can do nothing. But I think when the implementation when we have the implementation of this new technology, we can work together. We try to work together with some IT engineers from SAMPS in some research.
Okay, good, because we've got some thoughts about that, so I think we'll have a talk about that afterwards. Thank you. Okay, thank you for your attention to this session. And we've now got lunch at the same place as yesterday. I think you have to remember to grab a ticket, otherwise you won't be let in.